Welcome to Life with David. I'm David, and today we're continuing our bare metal adventure with the RP2040. A few videos ago, I promised some troubleshooting techniques for bare metal programming. However, I got sidetracked with elimination of the C, C++ SDK. However, now I can share various debugging tools without using the SDK or a separate debug probe. In addition, I'll examine assembly language interrupts to enhance the troubleshooting experience. So why don't you join me as we make bare metal debugging easier? I started using these debugging techniques in the mid-70s when the only computer you had was the one you were working on and it didn't have text output. There was no assembler, only the machine language you entered through the front panel. Things got much easier after I built a terminal and could use text and the 6530 TIM monitor program. These techniques may seem archaic in these days of debug probes and programs, emulators, and other aids, but they work for simple programs. I'll demonstrate these aids using a revised version of the PIO program I demonstrated in Chapter 7. I'll put a link in the description below. I've streamlined the program by modifying the sections so that the RP2040 initializes out of flash and the PIO and troubleshooting routines execute out of static RAM. In the version of this program featured in the last video, I had a short memory copy section at the beginning of the code that moved the bulk of the code, including the initialization of the system clocks, from flash into static RAM where it executed. However, as noted by a viewer, this results in the relocation of this code being performed at a much slower clock frequency and thereby taking longer. It also results in code that's only used once, occupying valuable static RAM. It's much more efficient to execute the one-time initialization out of flash and then move the balance of the program into static RAM. That's how I've organized this version. I've renamed the section that executes out of flash as reset. The section that executes out of static RAM has been renamed main. I'll include links to all the code used here, including the revised linker script, vector table, and makefiles in the description below. The most basic troubleshooting tool is the onboard LED. Here I've set up a routine to turn the LED on or off. Within the program you're debugging, branch to these routines at the desired breakpoints. If the LED turns on, you know that the program has at least reached that breakpoint. Continue moving the LED branch deeper into the program until the LED doesn't light, and now you have narrowed down the problem. However, what if you want to check for branches? It'd be nice to add additional breakpoints, but usually execution is so fast that you can't see if an LED is lit before it turns off. So I've developed several blink routines. You can insert a branch to the blink routine at the desired location and see a single short blink, 2 quick blinks, or a long blink. You can count blinks and look for expected patterns to help determine the flow of the program. A simple blinking light will help you find where the problem is occurring, but not necessarily why. Luckily, the RP2040 has 2 UART channels for serial communications. This opens up the door to examining register and memory contents. However, that increased capability comes at the cost of more complex programs and overhead. Let's get into the details. The initialization of the UARTs is outlined in section 4.2.7 of the RP2040 datasheet. In Chapter 3, where I used the SDK to get started, I followed the order of the initialization steps presented there. However, when I didn't use the SDK, I had to set the peripheral clock before I brought the UART out of reset. This wasn't an issue when using the SDK since the UART had already been initialized once before I even got started. Since I've already covered the UART initialization in detail in Chapter 3, I'll go through it pretty quickly here. For more information, please review Bare Metal Adventures Chapter 3. I'll put a link in the description below. After we start the crystal oscillator, I'll set the peripheral clock for UART 0, reset the UART 0, and then deassert the reset. I'll verify that UART 0 has been successfully brought out of reset and then enable the entire UART, including receive and transmit. Next, I'll set the baud rate to 115,200 to match my UART to USB adapter. I'll set the word length to 8 bits and enable the receive and transmit FIFOs. Finally, I'll connect UART 0 to pads 0 and 1 using function 2. At this point, the PIO is initialized and the main program is copied into static RAM. The memcopy routine then transfers the program pointer to the start of the main program where the PIO program is loaded into PIO memory. Let's look at how you can use blinking lights to track the program's progress. Here I've put a single blink for each time that a PIO instruction is copied into the PIO memory. There are 16 instructions, so there are 16 blinks. Next, I want to make sure I finish setting up the PIO, so I'll add a long blink after I set the top and bottom wrap values. Finally, I'll use 2 quick blinks to verify that the PIO state machine has been enabled. At first, I thought I could locate the troubleshooting routines in Flash, but that proved cumbersome since you can't use a simple BL instruction to access them. The RP2040 uses ARM thumb mode, and the shorter 16-bit instructions don't let you bounce all over memory with a single instruction. To simplify the debugging process, I've located all the troubleshooting routines in static RAM. Now let's get into the text-based debugging tools. The first is the register print. This will print the word contained in register 0 to the screen. First, I'll preserve the registers and then load register 4 with the contents of register 0. Register 5 will get the length of the word in bits, in this case 32. Since I want to print the most significant nibble first, I'll subtract 4 bits from the total width of the word, leaving a value of 28 in register 5. Then I'll refresh the original value of register 0 using the contents of register 4. I'll shift register 0 right 28 bits to move the 4 most significant bits down to bits 0 through 3. I'll load a bit mask of 1111 binary into register 1 and then AND it with register 0, which will isolate bits 0 through 3 of register 0. Now we're ready to convert the number to ASCII. If the nibble is less than 9, then I'll add 30 hex to convert it to 30 through 39 hex, representing ASCII codes 0 through 9. If the nibble is greater than 9, I'll add 57 hex to convert it to 61 through 66 hex, representing ASCII codes A through F. I'll output the character in register 0 using the UART 0 out subroutine. I covered that routine in detail in Bare Metal Adventures Chapter 3. Then I'll check if we've converted all of the nibbles. If so, we'll return, but if not, I'll branch back to regprint 0, where I subtract another 4 from the number of bits left to convert. After refreshing register 0 with the original word, I'll shift over 24 bits to convert the second most significant nibble. I'll continue converting nibbles into ASCII until there are no more nibbles to convert. You can see an example of this routine at work during the loading of the PIO program. I also use the print carriage return line feed and print space to help format the output. Another debugging tool is the ability to examine the contents of memory. Here I've developed 2 routines, one to convert an 8-character ASCII word into a 32-bit binary word, and the other to use that word as the memory address to retrieve the contents and then print it out. I'll go through the ASCII to hex routine first. I'll preserve the registers and then I'll load the number of ASCII characters to be received into register 2, in this case 8. I'll clear register 1, which is where I'll build the binary word. Then I'll wait for an ASCII character to be entered. After the character is received, I'll save the original character in register 3. Then I'll use various comparisons to determine if the character is 0 through F. I'll convert that character to its nibble equivalent. Basically, it's the reverse of the print register routine. The nibble is stored in register 0. I'll add that value to register 1, where the 32-bit word is being built. I'll decrement the number of ASCII characters expected and then check to see if we're done. If not, I'll shift the word we're building left 4 bits in preparation to receive another nibble. I'll restore register 0 with the original character and then output it as an echo of the input. I'll repeat the process 7 more times until the binary word is fully formed in register 1, and then I'll return. The memory examination routine is very straightforward. Here I print a carriage return in line feed and then call the ASCII to hex routine to input the 4-byte address. Then I'll move the resulting binary word into register 0, where I'll start a new line and repeat the memory address. I print a space and then retrieve the memory contents in register 0. I'll use regprint to output the character of the screen, then I'll do it again. This provides a basic suite of tools to help debug a program. However, we can enhance these tools by using interrupts. That way, we can break into a program that is frozen to see where it is and what condition it's in. But first, we have to understand using interrupts with assembly language. I've covered PIO interrupts using MicroPython and C in episodes 19 and 20 of the PIO Chronicles. I'll put a link in the description below. In many ways, assembly language interrupts are more straightforward than higher-level languages. There are just a few concepts to understand. Interrupts are a subset of a broader class called exceptions. Exceptions describe any condition that requires the processor to stop what it's doing and do something else. Section 2.3.2 of the Cortex-M0 Plus Devices Generic User Guide lists 7 types of exception, including reset, hard faults, and interrupts, to name a few. I'll leave a link in the description below. The roadmap for what the processor does when it receives an exception request is provided by the vector table. Each word in the vector table points to an address where an exception handler routine lives. The location of the vector table depends on the type of the exception. For instance, the first 16 words correspond to the stack pointer, the reset vector, non-maskable interrupt, hard fault, and other processor-related exceptions. Words 17 through 48 point to the interrupt handlers for the peripherals as described in the NVIC or Nested Vector Interrupt Controller. These are shown in section 2.3.2 of the RP2040 datasheet. I briefly introduced the vector table in Chapter 4 of Bare Metal Adventures. At the time, I said we only needed to worry about the first 2 locations. Now we're going to get into more detail. What happens when the processor receives an exception request? Well, the first thing it does is to memorialize the current state of the processor by pushing 8 words of register data into the main stack to provide the information needed to return the processor to what it was doing before the interrupt request was called. This is called the stack frame, and per section 2.3.6 of the Cortex-M0 Plus Devices Generic User Guide includes registers 0 through 3, register 12, the link register, the program counter, and the program status register. Then the processor goes to the vector table and uses the address pointer to branch to the exception handler associated with the exception request. In the land of bare metal, we have to write our own exception handler. The exception handler instructs the processor how to take care of the needs of the device that triggered the interrupt. After the exception handler program has finished, the processor will use the stack frame to return to what it was doing before it was so rudely interrupted. I want to use an exception request to output the status of the processor on demand. An interrupt will be able to break into a program that has gone rogue and has locked up. I have a choice of several different methods to generate an exception request. For now, I'm going to focus on interrupts generated by the NVIC peripherals. I could use a GIO port, an I2C signal, or a UART signal. Since I'm already using UART 0, I'll use that. I'll use the semicolon to tell the interrupt handler to print the registers. Typing any character will trigger a UART 0 interrupt, and the processor will enter the interrupt handler. At the beginning, the handler will check if the semicolon was typed. If not, it will return and let the processor go back to what it was doing. However, if a semicolon was typed, it will grab various register locations and output them to the screen before letting the processor do what it was doing before. But before we can use any interrupt, we have to set it up. Let's go through the modifications needed to our reset section to initialize the interrupt for UART 0. Originally, we chose to have the UART receive and transmit FIFOs enabled. This allows seamless input or output of serial data even if the processor or the target device is busy. However, since we want immediate attention when we press a key, I'm going to disable the UART FIFOs by clearing bit 4 of UART LCR-H and then set the receiving interrupt mask so we throw an NVIC exception when there is a character in the receive holding register. I've just commented out the original script in case we want to revert back to using the FIFOs. Note, we use either one or the other, but not both. Next, I've added code to initialize the NVIC for handling UART0 interrupts. As you can see from section 2.3.2 of the RP2040 datasheet, the UART0 interrupt is IRQ20. I'll enable that interrupt by setting bit 20 of the NVIC ISER register. The UART0 interrupt service routine, or ISR, will be located in the main section. This ISR is a little more verbose than normal. If many interrupts can fire in a short time, then we have to get more creative in making them short and giving them priorities. But since this is the only interrupt for this application, and I'm still learning, this will work okay for now. Because I need the virtual memory address of this routine for the vector table, I'll declare it as a global thumb function. Then I'll push the value of the link register to the stack. It's important to note that the value in the link register immediately after the processor enters an ISR is not the return address like it is for branches, but rather is an exception return value. This exception return value specifies whether to return to the thread or handler mode and where to get the return state, either from the main or process stack. There are more details in Table 2-12 of the Cortex-M0 Plus Devices Generic User Guide. Also note that this link register value is not the same as the link register value that was memorialized in the stack frame just prior to entering the handler routine. In order to compare the pre- and post-interrupt link registers, I'll stash the post-interrupt link register into R3. Since the ISR was entered because a character had been received in the receive holding register, I'll directly read the register instead of branching to the UART0 in routine. Then I'll isolate the 4 least significant bits and then compare it to 3B hex, which is the ASCII code for semicolon. If it's not a semicolon, then we'll return by popping the link register, which contains the exception return value, into the program counter. This exception return value tells the processor to use the stack frame to restore its status back to what it was just before the interrupt request. However, if it is a semicolon, we'll continue to output register data to the UART. I'll use the stack frame and current processor information to get the program counter, registers 0 through 7, the stack pointer, and the link register contents just before we entered the interrupt handler routine. I'll also output the link register just after the interrupt handler was entered, which will display the exception return value. This process is pretty straightforward and is done brute force style, one after another. Basically, I start a new line, output a label for the register, load the value of the register into register 0, and then output the register contents that's in register 0 to the terminal. Then I do it for the next register. I've put together a little routine that allows me to print 4 bytes of ASCII data in one word. I'll use that to display short messages as labels to the data. The short messages are defined using the .equ directives. I'll get the value for registers 0 through 3, the program counter, and the link register before the interrupts from the stack frame. The values for registers 4 through 7 and the link register after the interrupt represent the status of the processor as it entered the ISR. Now we have to tell the processor where to find this interrupt service routine using the vector table. Remember, the NVIC interrupt for UART0 is number 20. I'll edit the vector table and enter the label of the UART0 ISR in that location. During the compilation, the linker will put the address pointer for the routine in that location. Remember, This is a thumb function, so when we look at the disassembly file, the address will have bit 0 set. Let's try it out. Here I've written a short loop where I simply move various values into registers 0 through 7. For this demonstration, those values represent the register number. I'll start the program, and after the loop has been entered, I'll tap any key other than the semicolon, and the processor is interrupted, but almost immediately returns to what it was doing. However, when I type a semicolon, the processor status is output. If we look at the disassembly file, we can see where the processor was when the interrupt fired by using the program counter. Here are registers 0 through 7 and the stack pointer. The previous link register points to the last branch the processor took, and the current link register displays the exception return value. I think this counts as an overwhelming win. Thanks for joining me today. This time we developed several tools for debugging bare metal assembly language programs. We also explored assembly language interrupts on the RP2040, including interrupt initialization, developing an interrupt handler, and modifying the vector table. Now I have the means to troubleshoot future, more complicated bare metal programs. And I hope to get into more complicated programs in the future, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!